No discussion of pharmacokinetics, even the very basic principles of pharmacokinetics, would be complete, at least to me, if we don't include the so-called pharmacokinetic parameters. Now, if you've watched our rundown on the four main pharmacokinetic processes, you would know that a lot of what we have been covering and talking about so far are qualitative things. Like in absorption, we know that drugs go from the site of administration to the blood, or in metabolism, active molecules are metabolized into inactive molecules ready for excretion. And those are really things that tackle questions of what, right? What happens, okay, or how does it happen? But the quantitative aspect was not really touched a lot, because if we ask how much has been absorbed, how much has been eliminated, how fast is it eliminated, those are also crucial questions, because in practical applications, only if we have that quantitative aspect will we be able to predict things like how much of the drug will you be giving to a patient, how often will you be giving it, should you adjust your every 6 hours dose to every 4 hours, and why does it go like that? Now, this video, and I will cut, in fact, this discussion into two videos because it might be too long if I'll discuss this all in one go. But still, those things of practical use are way too complicated for our level. All I want to do here is for people who have no idea yet what the implications and meanings of bioavailability, volume of distribution, and the rest are. This is, we could say, a primer for you guys. Now, if this is something you already know, probably this is not a video for you. But with that, let's start with the first pharmacokinetic parameter. Bioavailability is essentially the amount of drug that enters the bloodstream successfully. And just to add context to that, if you watched my absorption recordings, we know that not every single drug molecule that is administered to us will successfully reach the blood. Particularly, since passive diffusion is the most common route of absorption, only the unionized forms of the drug can pass through. And the ionized forms, the ones with charges, cannot really go inside. Now, if we assume that all of the molecules go inside, then that would mean that the bioavailability is 100%. But since I just said that such is not possible, then this is not attainable with most routes like oral or rectal or buccal or intramuscular. However, we do know, and I have also mentioned this before, that if you administer your drug intravenously, there's no more barrier to speak of, because if let's say this is the syringe, and then you plunge your drug molecules directly to the blood or directly to the vein, then there's no barrier anymore. So it's like saying that compared to any other route, the amount of drug molecules that successfully reach our systemic circulation is the highest in IV. That's what makes it the denominator in our formula. It's a sort of standard. Okay. And so again, let me repeat here, or let me just mention, okay, that bioavailability F is equal to the area under the curve of the route that you chose over the area under the curve of the IV. Again, this is at the denominator since it serves as the standard. The area under the curve is something that we get elsewhere. This is something more mathematical rather than pharmacokinetic. So probably in more detailed accounts or discussions of your pharmacokinetics class, if you have one, then that's how you will attain the area under the curve. But let's not dwell on that. Let's dwell instead on the fact that if I just said that any area under the curve in the IV route is greater than the area under the curve of the one in the numerator, we know that if the value at the bottom is always higher than the value at the top, then that means that your F will always be a fraction. Or if you can multiply that by 100, if this is smaller than this one all the time, then we know that the bioavailability computed will always be lower than 100. So let's say that, let's just skip the actual computation. You have computed a bioavailability value of 30%, or if you don't multiply it by about 100, you get an F of 0.3. That only means that 30% of all the molecules that you initially took got inside. And of course, that means that the rest, the 70%, did not successfully make it. Okay, and you should know that is important because, like, maybe we could throw in the most radical example. What's the point of taking a drug that is only 0.01% bioavailable? It's like you didn't take it in the first place because it didn't even get inside you, technically, right? That is the practical application of bioavailability. And we ought to know it for any drug that we want to take or study at least. Next, we have the volume of distribution or VDN. This probably is the parameter I will discuss before cutting the recording here. So the volume of distribution, very crudely put, is the amount of fluid that can uniformly handle all of the dose that was given to the patient. Now, what I have seen in reading textbooks and attending classes as a student, and even in trying to teach it in a very few times I did this in real life, I taught this in real life, it was very difficult to imagine it. And eventually it becomes something like an abstract topic. Like, imagine you are a person that is the size of a house. You should have this, and like those things are not realistic. And it ends up being circular, not really making the point. So for me, instead of defining this really, let's just give examples so that we could probably, well, hopefully for you guys, grasp the importance of the VD, okay? So to do that, I put here a demonstration showing two drugs, like drug A, B, the one in yellow, and then the green one, let's just call it drug B, right? And the formula of the VD is AB over CP, wherein AB is the drug dose, basically all of the dose you took, over CP, or the plasma concentration, or the amount of drug that is currently in your bloodstream. So let's say I have this diagram, okay? First thing is, if any beginner, anyone who has never heard of VD, is to understand VD, first, he or she should know where this is in imagination and where this is. Well, think about it. AB is said to be the drug dose. This is basically everything. So let's imagine that we have drug A lot of it is currently in the blood, and the rest are in other organs, okay? The heart, the muscle, whatever. And we know that the process of going from the blood to the other organs is the process of distribution, hence this arrow. Where is the AB there? Well, I just said that AB is all of the dose. So you compute all of the dots here. That's the entire AB. Or for drug B, that's also the entire AB. But the plasma concentration is the amount of drug in the blood. So this is that part, right? So you only count the particles here, and that's going to be the CP. So AB, all of this, CP is this. Now, knowing that, why not compute really for the VD of A and B? And then let's make some interpretations later. So for the VD of drug A, that would be everything, right? AB is you count everything. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the AB. Then how many of the particles are still in the blood? It's this, right? 1, 2, 3, 4, 5, 6, 7, 8. So 10 divided by 8, that's not going to be a whole number. That's like 5 over 4, right? So that's 5 over 4. Or something just like 1 point something, right? So can we just, let's say, round it down to 1.0, just so we could interpret it later. It's like 1.25, if I'm, yeah, correct me if I'm wrong, but yeah, it's 1 point something. How about for drug B? So the VD is going to be like, let's count everything. 1, 2, 3, 4, let's count that as a dot. 5, 6, 7, 8, 9, 10, 11, 12. And then we count the dots here in the blood, 3. 12 divided by 3 is 4, okay? So again, rounding things up to whole numbers, our VD for drug A is 1 and VD for the drug B is 4. What does that mean? Obviously, if you want things to be not really complicated first, you just say between drug A and drug B, which has a higher volume of distribution. Obviously, the volume of distribution for drug B, 4, right, is greater than the volume of distribution for drug A. But you know, if you're asked, and this is sometimes a difficult question, What does that even mean for drug B? Yeah, you have a greater VD. What happens in imagination? For some people, it's really blank. But luckily, we have here a graphical representation. So, what can we really say here? Remember, the definition of distribution is the transfer from the blood to the other organs or compartments in the body. And if I ask you here, in the others, like the area where things are supposed to be distributed, between drug A and B, which has more of it in the other parts? Obviously, you can see that the molecules of drug B are much, much more than the molecules of drug A. Or should we say that drug B is much better distributed than drug A? And that's why anything with a greater volume of distribution will, in essence, be more distributed. And anything with a lesser volume of distribution will not be distributed. And the implication is anything with a lower VD, that would mean that more of its drug molecules will be stuck inside the blood. And as you know, whether or not we know, whether or not the drug can traverse through membranes or be distributed or not will be a great deal, because we know that it is only the free drug that can give effect to the body. And it is also the free drug, the distributed one, which could be easier excreted. Okay. But that's for now, and we will just continue the rest of the pharmacokinetic parameters in a separate recording.